Good afternoon. This set of notes is kind of an addendum to Unit 6, but we're going to be using it as a bridge in between Unit 6 and Unit 7. There are a few items from Chapter 10 that will be helpful, and they'll help us understand and make connections between some of the things that we've already learned. One of those topics is inter versus intramolecular. Take a look at the prefix here. Intramolecular bonding refers to forces within molecules. On the other hand, intermolecular bonding refers to forces between molecules. It's been helpful for me to think about those parts of those words and associate them with other words that I know that have the same parts. A term like interstate highway. So I-94 is a major interstate highway that runs through Chicago. Interstate means that it goes between states. When you're riding on I-94, you can go to other states like Wisconsin or Indiana, from state to state. Another word, internet. So that's a way of networking between yourself and people outside of your immediate network. We do have within the school an intranet. That's something that the faculty and staff use to communicate only with other people who are in the building. We post worksheets on there and things that we want to share within our network. You might be able to think of some other terms that have inter and intra in them, and that can help you remember those terms. As they relate, however, to bonding and molecules, I'd like to draw your attention to this diagram on the right. Here we have a molecule of H2O, and the bonds within the molecule are these purple ones. These are the intramolecular bonds. We've already learned quite a bit about these bonds. You know that they're covalent bonds because they are between two nonmetals. You know that they're polar covalent bonds because oxygen is more electronegative than hydrogen. What we haven't talked about yet, however, is the forces that occur between two different molecules of water. These forces are the intermolecular bonds or intermolecular forces. These forces are actually quite important. Changes in states are due to these intermolecular forces. So the reason that water melts at a certain temperature, boils and turns into vapor at a certain temperature, that has nothing to do with the forces inside of the molecule proper, but instead that has to do with the forces between the molecules. Let's remember something about change of state. When molecules change state, recall, they do stay intact, right? So it's not like when water boils, you make some free oxygen and some free hydrogen. That doesn't happen, right? When water boils, this molecule will separate from this molecule. They will both become a vapor, but they will still remain the intact molecule that is water. So changes in state are due to changes in the forces that are between the bonds. So they're actually quite important. There are three types of intermolecular forces that we need to memorize. The first of the three, type 1 of 3, intermolecular force that we need to memorize is called a dipole-dipole attraction. You know this word dipole. Well, dipole-dipole means if you have two of those molecules, then they will attract to one another. An attraction between the positive end of one molecule with the negative end of another molecule. Here are some molecules that we should recognize as polar. So how do they play into a dipole-dipole attraction? Let's look at the diagram on the left. If you have a polar molecule, that means you have a molecule with a negative moment and a positive moment. And when it approaches another molecule with a negative moment and a positive moment, they will align their attractive forces. That means the positive side of one will be attracted to the negative side of the other, and likewise. Here's another way they can try and align their attractive forces. The negative side of one and the positive side of another pull towards one another. They will also repel their like sides as such. These types of attractions and repulsions that occur between polar molecules are known as dipole-dipole attractions. The second of the three types is called hydrogen bonding. Now, hydrogen bonding is really an especially strong dipole-dipole attraction in which a highly electronegative atom, fluorine, oxygen, or nitrogen, is bonded to a hydrogen. Since fluorine is the most electronegative atom on the periodic chart and oxygen is right behind it, nitrogen is also highly electronegative. Sometimes we just refer to them as FON, the highly electronegative atoms, the ones in that top right-hand corner on the periodic chart atoms. And when any one of those is bonded to a hydrogen, that molecule is able to participate in a hydrogen bond. Here we can see in the diagram water participating in hydrogen bonding. Water has an oxygen and a hydrogen bonded together. Remember, the highly electronegative oxygen is bonded to a hydrogen. So anytime we see that in a molecule, we know that this polarity, this electronegativity difference, this OH, is going to allow this molecule to have hydrogen bonding. We can see when many molecules come together, the oxygen side, highly electronegative, and the hydrogen side of an adjacent molecule have a strong attraction. This particularly strong attraction is a type of dipole-dipole force. It means both of these molecules are polar, they have a dipole moment, and they're attracted to each other, but this is a particularly strong attraction when it contains hydrogen. Hydrogen bonding has a big effect on molecular properties. Why is hydrogen bonding so strong? The high electronegativity difference maximizes the bond dipole. When it's a hydrogen bond and it's got F, O, or N, that really maximizes the difference between the hydrogen and the other element. Hydrogen's small size, number 2, also allows for a very close approach of adjacent molecules. So it allows the force to be acted upon because the molecules can get very close to each other. In this diagram, we take a look at elements in period number 2. That's the second row of the periodic chart. Period number 3, 4, and 5. So if you think about this, visually we're moving down the periodic chart. Period 2 is the period that has oxygen in it, and fluorine, and nitrogen, and carbon. They're all in the second row of the periodic chart. And you can see that in the molecules here, each one of them is binding with a hydrogen. The strongest hydrogen bonds have the highest boiling points. What does that mean? It means that elements that bond very strongly together through hydrogen bonding, such as water, are difficult to boil. Right, that means vaporize. So when these molecules are in contact with one another as a liquid form, they do not want to separate and form a vapor. It takes a lot of energy to turn water into a vapor. It takes slightly less energy to turn hydrogen fluoride, this ammonia, and finally this methane. So as it is with hydrogen bonding, molecules are held together more strongly when they can hydrogen bond, and they are bonded to a FON. one of the three most electronegative elements on the chart. Notice that even though carbon is in the same row, it doesn't have that electronegativity difference. There's no polarity here. And we also see a significant decrease as the molecules become larger and larger and larger. So larger molecules have a hard time fitting close together. So it's best for smaller molecules that are highly electronegative. They form the strongest hydrogen bonds. Or that water has a high surface tension. This is the reason why. Water molecules have hydrogen bonding, so they're attracted to one another. They hold together in sort of a network. And at the surface of that network, since there's a lack of additional oxygen to hold on to, they hold to one another even stronger. And the surface tension of the molecules at the surface of any water is rather strong. You've probably seen this experiment before where a paper clip, which is 1 gram, can actually float on the surface of water. That paper clip is actually resting on a network of water molecules. They're all hydrogen bonding to one another. The same can be the third and final intermolecular force that we must know is called London dispersion forces, also known as van der Waal forces. These are the weak attractions between molecules with instantaneous dipoles. What you're learning here is all molecules have some instantaneous dipoles, not a moment, less than a moment, an instant. This occurs in all molecules, whether they are polar or not, and particularly in larger molecules. One way to think about London dispersion forces is to consider a uneven distribution of electrons in something that has no charge whatsoever. And it certainly is not polar. This is a noble gas, it's helium. But what if you were able to observe that atom and take a picture? There would be some instance in which the electrons were lined up on one side of that atom, giving that side a negative instant, less than a dipole moment, and this side a positive instant. And what about other atoms that come in contact with this atom? Well, those atoms too will become instantaneously polarized, and so forth. Each element can instantaneously polarize the thing that is next to it. It's not a sustained charge. We would not call these elements polar. We would say that for an instant, they can experience an attraction. All substances exert forces on each other. So all substances can experience these types of London dispersion forces. Here's a diagram that sort of gives us an example. As electrons move around the nucleus, even though the elements themselves start out as nonpolar, a momentary non-symmetrical distribution can develop. Just for a moment, one side of the molecule becomes slightly positive. That produces a temporary dipole arrangement. So temporarily, we have a positive and a negative side in this molecule. Finally, it in turn affects neighboring elements. So this polarization will cause the neighboring atom to also become polar. These are London dispersion forces. Now, how do these all tie together? You've just learned about 3 new types of forces. Well, this slide gives us the relative strengths of inter and intramolecular bonds. And what you can see here is that the strongest forces that hold molecules together or push molecules apart are ionic bonds. Remember that lattice? We didn't even calculate lattice values. We only compared them, but lattice values are in the thousands of kilojoules per mole. We did calculate covalent bond energies, and they tended to be in the hundreds of kilojoules per moles. Hydrogen bonding that we learned about today is the strongest type of force that exists between molecules as an intermolecular force. Dipole-dipole is about relatively a tenth of the strength of a hydrogen bond, and relatively 1/10 of that strength would be a London dispersion force, the weakest by far. So these numbers here are approximations just to give you a sense of the relative strength of these 5 types of forces that occur. Is that when forces are really strong, the substances tend to have the highest melting points and boiling points. Remember, it's hard to melt and hard to boil ionic substances because the energy that holds them together is so great, it takes a lot of energy to break them apart. Covalent bond energies are strong as well, although they're not involved in change of phase, right? Because when something changes phase, the molecules tend to stay together. But hydrogen bond, dipole-dipole, and London do dictate the relative melting point and boiling point of compounds. Let's take a look at this diagram at the bottom. Hydrochloric acid, this looks like a highly electronegative bond, a covalent bond because it's between two nonmetals, giving this molecule a negative dipole moment and a positive dipole moment. This is a polar molecule. Here's another polar molecule. And in between these two polar molecules, there's an intramolecular attraction. What kind of attraction would you name it?